Hello and welcome. This tutorial video will demonstrate how to use CADWIND to wind an elbow fitting. As with any winding, there are 3 steps to follow. Step 1. Make the mandrel model. Step 2. Simulate the winding. And Step 3. Make the part program and start the machine motion simulation. Note that you will require CADWIND's high-end version to do this for yourself, as the other versions do not have the ability to make elbow mandrels. So, we will start at step 1 and make the mandrel model. To do this for an elbow with circular cross-section, simply click the File menu, then Create Mandrel, then Elbow Circular Cross-Section. In the window that appears, we will enter some parameters that tell CADWIND about the elbow mandrel's size and shape. I have prepared a diagram showing the dimensions of our demonstration elbow to show you. So, we just need to enter these dimensions into CADWIND. In this example, we'll be winding on a mandrel with a 200mm diameter, an opening angle of 90 degrees, and an inside radius of 300mm. I'll use 50mm linear sections. At the mandrel ends, CADWIND gives us a choice of different shapes, as it does with all mandrel creation, but for this elbow I will use extensions with a 250mm length, and I will use 80 equally spaced frames to mathematically divide the elbow into a mesh similar to a finite element analysis or FEA mesh. When ready, just click OK. CADWIND will ask you to save your mandrel into a file with an MDR extension, so you can load it again later. So just enter a file name, then click Save. Your mandrel model will appear on the screen in front of you. It's a fully 3D model, and you can rotate it with the mouse, zoom in and zoom out, just like you could with any 3D CAD software. Step 1 is now complete. Step 2 is to tell CADWIND the details of how to wind over the mandrel. Even though the elbow shape is quite complicated, this is easily done in the same way as for any other winding. CADWIND's powerful non-geodesic winding simulation will take into account the winding physics of any practical mandrel shape, and makes it easy for anyone to define a winding that you can be sure will work. First, enter details about the material, as usual. To do this, click the Winding menu, then Material. For this example, let's use 5 rovings, each with a width of 4mm, making a total bandwidth of 20mm. We will assume this winding will have a 55% volume fraction with an 800 grams per kilometer text carbon fiber toe. Next, enter the winding parameters under the Winding menu, Non-geodesic parameters. Note that the non-geodesic winding must be used over elbows and any other non-axisymmetric mandrel shape. Helical and polar winding are not suitable. For this demonstration, I will show that CADWIND makes it possible to use quite a low winding angle on an elbow. We will use 60 degrees winding angle. Of course, higher angles are just as easy to achieve. We will use a friction factor of 0.1, which is low enough to guarantee fiber slipping will not happen. In this example, we will keep the default turning zones and will not use dwell, although it is possible to alter the turning zones and also to use dwell if you prefer. When finished entering the winding parameters, click Start Winding. After Start Winding has been clicked, CADWIND will calculate the path that the fiber will follow across the surface of the mandrel. If the pattern number we entered is not physically possible, then CADWIND will use an alternative pattern from this table. From the table, simply select the pattern number which best suits your needs and click OK. If the selected winding pattern is possible, then it will appear on the screen shortly. If not, the table of alternatives will reappear and you should select another option. In this case, our selected pattern was possible, however, it has some problems. You can see here in the center of the elbow there are some gaps between the fiber bands. Elbow winding is more complicated than standard vessel or pipe winding, as the fiber angle must change in the radius section of the fitting, and the spacing between fiber bands is affected. In some areas, the bands are closer together, causing an increase in thickness. In other areas, the bands are further apart, and gaps can open as a result. In fact, if we check the results, we can see that the degree of coverage varies between 63% and 154% in this example. The areas of 63% coverage will have gaps between fibers. If we are winding a pressure fitting, this is usually unacceptable. This means that often for elbow winding, we must specify a degree of coverage much higher than 100% in order to guarantee that we have a minimum of 100% in all areas. So, I will repeat the winding, this time entering a degree of coverage of 150%. This time, there are no gaps in the winding. And if we check the results under the View menu, then we can see that the degree of coverage varies between 136 and 336%. So our fitting is completely covered this time. If the winding results are good, then step 2 is complete. The third step is called post-processing. This is the step in which we make the part program, and also we will see the simulation of the machine motion. To make the part program, click the Post-Processing menu, then Parameters. In the window that appears, there are some choices about how to move the machine and how fast to move the machine. All the choices should produce the same winding result, but the way in which the machine moves and the speed will change depending on the choices that you make. For example, if you have a machine with 2 axes of motion only, you should choose the Open Enveloping Cylinder calculation mode. This then will not try to move the cross carriage axis. To make the part program and start the simulation, click Control Data. It could take a few seconds to calculate the machine motions required for an elbow winding, as the path is complicated and there are no repeated motions, so the part program will be quite long. The simulation starts as soon as the calculations are finished. You can see the cross carriage doesn't move because we chose the Open Enveloping Cylinder calculation mode. You can also see that the delivery head must move a long way past the mandrel to achieve this winding using the Open Enveloping Cylinder mode. We can also check the winding time required under the View menu, Results window. In this case, the winding will take 18 minutes and 43 seconds. This is quite slow, so if you have a machine with 4 axes of motion, you might want to try a different calculation mode. To see a better simulation for a 4 axes of motion machine, we can return to the Post-Processing parameters, click Post-Processing menu, Parameters. Let's try the Enveloping Contour calculation mode this time. Click Control Data to start the simulation. This time you see CADWIND has used the cross carriage axis to move the head of the machine closer to the mandrel at the ends. This means that the carriage axis does not need to move so far, and it reduces the winding time. The Results window under the View menu tells us the machine requires 16 minutes and 5 seconds this time, which is about 3.5 minutes faster than before. Also, if you have a mandrel with a large opening angle and a low winding angle, there could be problems with the fiber touching the mandrel, as you can see here. CADWIND offers another interesting calculation mode option to try, which may be faster and may solve the problem with the fiber touching the mandrel. If we return to the Post-Processing menu, we can try the Constant Free Fiber Length calculation mode. This will keep the length of the fiber constant between the contact point on the mandrel and the last contact point on the machine head. If we choose a free fiber length of 250 mm, this will bring the head of the machine close to the mandrel and can often reduce the winding time and avoid the problem caused by the long free fiber length. You can see that the machine motions are much more complicated using the constant free fiber length calculation mode, and there is a higher risk of collision. If there is any collision, however, you will see it on the screen beforehand, so you have a chance to correct it and avoid it. The advantage with this calculation mode is that the distance travelled is reduced, so the winding can be completed faster, and the fiber will not touch the mandrel in the wrong spot like it did before using the enveloping contour calculation mode. The winding time using the constant free fiber length calculation mode is only 8 minutes and 42 seconds. So in this example, it is much faster than the other modes. So you can see that CADWIND makes elbow winding easy, and it gives the user many options so that he or she can produce a good winding solution for almost any elbow fitting possible. And this can be done on any winding machine, from 2 axes through to 6 axes of motion. If you have any questions about elbow winding, please feel free to send us an email or give us a call. Thank you.